Hi, this chapter is about ensemble learning. So this is the outline. And first of all, we're going to talk about what it is. What is ensemble? With one example, a random forest. And then we'll talk about three different ensemble approaches, bagging and boosting and mixture of experts. And usually when people talk about ensemble learning, they talk about bagging and boosting. But I think a mix of experts could be one of ensemble approaches. Okay, so this is the perfect chapter for a mix of experts. And then we'll talk about why ensemble learning works. And we'll talk about a couple of applications. Okay, first, you already know what random forest is, right? So random forest is based on the lot of descent trees. That's what a forest means. So we have lots of descent trees. So when we have a new sample, then we feed that sample to all the descent trees. And then each descent tree makes a decision. And we actually gather all these decisions from all the trees. And then we make a decision based on kind of majority. Okay, so that's random forest. So random forest is a perfect example of ensemble learning. So in this slide, we have only two descent trees, but let's assume that we have 50 descent trees or 100 descent trees, and all these descent trees are different. Then they can predict or they can make a decision, and then we gather all the decisions and then make a final decisions. That's random forest. And we can actually explain this ensemble learning with more kind of figurative explanations. Okay, first, we can think of a democratic principle. So people vote to elect officials or legislate. They are not actually appointed by one person. So all the people actually make a decision. Okay, and then we gather all these decisions and then actually we use majority vote. Okay, or we can use experts' opinions on some issues. Okay, something like several doctors for a diagnosis. So when one doctor is not enough, then we can discuss and we can get another opinion, second opinion, and third opinion. Or I think this is more familiar to you. When we search a restaurant in a new place, then we can check some reviews. Okay. Or when we're interested in one movie, film, then we check the reviews and rate. So this review rate is based on the lot of people. They actually put a rate, and then we gather all these rates, and then we take an average, and that's the opinion of the crowd. And it has been successful in many machine learning problems too. Okay, so in machine learning, let's assume that we have only three models, 1, 2, 3, and each model has different kind of classification boundaries. So model 1 has these boundaries. So this one is class 1 and class 2 and class 3. And model 2 has slightly different boundaries like this. And model 3 has also different boundary. But let's take a look at this example. This example belongs to class 3 according to model 1. But in model 2, it belongs to class 2. And in model 3, it belongs to class 2. So even though model 1 says this is class 3, but model 2 and 3, they say this is class 2. Then based on this combination, the final decision would be class 2. That's simple example of ensemble learning. So we simply take average of these decisions or the boundaries, and then final decision is something like this. This is final decision. This is what ensemble learning does. Okay, so remember the model 1 and 2 and 3, they are all different, and we just combine all of them to make the final decision. Okay, so let's talk about ensemble learning and machine learning in detail. So ensemble learning, ensemble of classifiers is a set of simple classifiers. Okay, and the final decision is based on the combination of the classification of new example. Okay, so we have lots of simple classifiers, and then we actually classify with all these classifiers, and then we just combine. Okay, And the random forest is a perfect example, as I said. And taking simple algorithms and transform them into a super classifier without requiring any new algorithm. This is a beauty of ensemble learning. So ensemble learning can be applied to any kind of classifier. So we have a linear classifier, or we have KNN, or we have naive-based classifier. Ensemble learning can be applied to any classifiers. Even we can actually combine different kind of classifiers. So the model 1 is based on the KNN, the model 2 is based on naive-based classifier, and model 3 is based on the linear classifier, etc. So we can combine all of them. So ensemble learning is not just about one learning algorithm. So this is process. Train multiple simple classifiers, and it doesn't have to be simple per se. Okay, so if you have a one classifier, then you can make more classifiers. And then we run the classifiers and test the sample independently. Okay, we can run all these classifiers in parallel and then classify by majority or weighted sum. It depends on the problem. Okay, so if it is a classification, then each classifier has its own decision. Then we can actually take a majority vote, or we can use weighted sum of all the probability, and then we can find the maximum. So it depends on the task, and it's your call, basically. Okay, then we can try many different ways for ensemble learning. Depending on individual classifiers, we can choose many different classifiers. Okay, as I said, we can try the same kind of classifiers a lot, or we can try many different types of classifiers at the same time. And then we can select training data. So when we have 100 data samples, the training data samples, then we can use just 70% of training samples to train a classifier. So this 70% can be randomly selected. Then we can train a lot of classifiers based on the 70%. So sampling with replacement or random subspaces. So random subspaces means when we have 30 features, then the first classifier can be trained with just 25 features, randomly selected 25 features. And second classifier can be trained with 25 features too. So it's randomly selected. And when we have training samples like this, then this is features and this is samples. Then we can select samples randomly, or we can select features randomly. So we can train the individual classifiers with the different sampling. Okay, and also classifiers can be heterogeneous too. And next one, the specific procedure to train ensemble members. So we have a bagging and we have a boosting and we have a mix of experts. So we're going to talk about these specific procedures in this chapter. And the last one is about the combination rule for obtaining the ensemble decision. So we can use a majority vote or average, or sometimes we can use a mean or max. Okay, so depending on these options, we can build up a new ensemble learning for your classifier. Okay, bagging is the first procedure to make ensemble learning. So random forest is a good example of bagging. And bagging or bootstrapping aggregating. So bagging, okay. And the bagging is quite a simple ensemble learning procedure. So given an original data set consisting of n data points, then we're going to generate m data sets, each of size n. And this dataset, each dataset is created by drawing endpoints at random from X with replacement. For example, in the first dataset, maybe we might have X sub 1 twice or 3 times. We don't know, right? Because it's based on the replacement. So once we select one data point and then we put it back to the dataset and then we select randomly the next point. Then let's talk about the training and testing. So given m datasets, then we can train m models f sub m. This is a training procedure. This process depends on what kind of classifier we have. If it is KNN, then we don't train the model, right? But if it is a naive based, then we have to estimate the distribution. And if it is a neural network, then we have to find the parameters of the neural networks. Anyway, depending on the classifier, we can train. And then testing is also quite simple. So prediction of the committee is defined by this. So this f sub m is individual classifier, and then we run all the classifiers in parallel. Okay, and then we take an average. This is the prediction of the committee. And when this is a regression problem, yes, this is perfect. But when this is a classification problem, maybe we can use this average or we can use majority fault too. And here is quite an interesting statement. If errors due to the individual models are uncorrelated, so which means f sub m, f sub 1 and f sub 2 and f sub m, they have their own error. And then if these errors are uncorrelated, okay, which means these models are kind of uncorrelated from others. Okay, then the error of this committee is quite small compared to the average error. So average error can be calculated in this way. So this is an error because this one is estimate and this one is target and this one is expectation of error, expected error for each model. Then we take an average of this expected error. So that is average error. So we trained all the models. When we calculate the errors, so we have error 1 and error 2, error m. And then we take an average. Okay, that is average error. And then the error of committee is m times smaller than average error. This is huge. So if we increase the number of models, then the error goes down again and again. But practically, this is not possible because this condition will not be satisfied. Think about this data set. We have m data set, but even though we select these endpoints randomly with replacement, but still, this selection is from the same data set. And then m data sets are quite similar. That's the problem here. So when we train these models, m models, they're all trained on the similar data set. So these models are quite similar, not completely different kind of decisions. Okay, then this one is not satisfied, so we cannot achieve this much improvement. This is not practically possible. But when we select the data sets, then the data sets are a little different. Then the models are a little different. So from this difference, even though these are not perfectly uncorrelated, but still there is a little uncorrelatedness between the models. So we can decrease the error. Not this much, but still there is improvement in the performance. And then the next procedure is boosting. Boosting is a little more sophisticated than the bagging. So bagging is quite simple, right? So we train the models in parallel. Okay, and then for testing, we just run all the models in parallel. And then we just combine the results. That is bagging. But boosting is not in parallel. Okay, so we combine multiple base classifiers in sequence. Okay, so the base classifiers are trained in sequence. So each base classifier is trained using a weighted form of the data. So every time we change the weight of the data samples. And these weights are adjusted according to the performance of the previous classifiers. So basically, new learners focus on the instances misclassified by previous classifiers. This is the beauty of boosting. So the first model trained. Okay, and then we actually check the weight. for the samples. So let's say we have x1 and x2, x3 and x4 and x5. And then the first classifier is perfect with these samples. Then we put more weights on x3 and x5. So we train the second model with a different weight. So these ones are more important for this guy. And then for the third model, when the second model is not perfect for x sub 3, then we put more weight on this sample and then we train f3. And then we train the next model and next model and next model. So finally we have f sub m. So this f sub m depends on the previous classifiers. And this one depends on the previous classifiers. So when we train the models, then all these models are in a sequence. There is an order. Okay. And this is one example of boosting, which is auto boost. So we initialize the weights for the samples based on the uniform distribution. So all the samples have the same kind of importance at the beginning of this procedure. And then first we train the model to minimize the weighted error function. So for the first iteration, this one is just error because the weights are the same. Okay, so this is what we want. This is uniform and this one is an error. So when the prediction is not exactly the same as the target, then it is 1. Otherwise, it is a 0. So we are focusing on all the misclassified predictions. And then calculate the weight for the classifier. So this one is about the classifier. So M is about the model and N is about the samples. Look at these equations. If error is high, then the alpha is small. So if error is low, which means the classifier is good, so alpha is high. Okay, so alpha means how good the classifier is. And the error can be defined in this way. So this is the sum of all the weights, and this one is a weighted sum of this indicator. So we are focusing on the wrong prediction with the weight. So if the classification is perfect, then this one will be 0. Okay. And then for the next iterations, we update the weight based on this. So we actually multiply this one to the previous weight. So we've been updating this weight with the sequence of the models, and then we multiply this one. So this one is about the classifier, and this one is about the sample with that classifier. Okay, so every time we know how to update the weights and then how good the classifier is. Okay, then the prediction is simple. We can actually apply all the models in a parallel. So because we have the weight for the classifiers, so we run these classifiers in parallel and we multiply these weights and then sum. That is the prediction of X with auto boost. Auto boost is slightly better than the bagging, but it's complicated than bagging. So bagging is more popular than auto boost. But sometimes auto boost is better performance-wise.